So we were into the interesting derivation of the energy equation. It may sound a little longish, but I would implore upon all the students to derive the way I have derived. I have tried not to skip any step so that you are with me all the time. Okay, please do derive. It's once in a lifetime, at least you should derive once. Okay, so we were here, we had derived this equation. Now we were just about to see that H in the form of temperature. So to get that, I need to write H as equal to Cp into T. From thermodynamics we know that. So if I do that, H is equal to Cp into T, and my equation rho dH by dt equal to K into dou squared T by dou x squared plus dou squared T by dou y squared plus dp by dt plus phi plus q dot triple prime. Now if I substitute H is equal to Cp into T and Cp is constant, so rho Cp dt by dt is equal to K into dou squared T by dou x squared plus dou squared T by dou y squared plus dp by dt plus phi. Remember, this is the viscous dissipation term which had all the velocity gradients. This is what you can see, that viscosity and velocity gradient, viscosity, velocity gradient. This is stretching, this is stretching, this may cause either rotation or angular deformation. Okay, so depending on the plus or minus, plus q dot triple prime. So if you divide through, this is the whole energy, this is what we were up to. We can see that now this is the energy equation. Okay, and this, if you expand this, rho Cp instead of dt, let us expand this, dou T by dou T plus u dou T by dou x plus v dou T by dou y is equal to K into dou squared T by dou x squared plus dou squared T by dou y squared plus dp by dt. This is the total derivative of the pressure plus viscous dissipation term plus q dot triple prime. So this is the total derivative, that is the temperature is varying with time and this temperature is varying with x and y by virtue of convection. If you have to physically feel this, if I consider this room, when I am entering into this AC room with a velocity u, I experience a velocity temperature gradient of del T by del x, that is the convective term. But someone while entering, someone hits me with an ice ball, so that I will experience instantaneously a temperature change, that is dou T by dou T. So these terms are because of the temperature variations, because of the by virtue of convection, that is u and v, because they have the velocity, and this is instantaneous temperature change. So this is convection term, this is heat transfer by conduction, and this is pressure work, and this is viscous dissipation. You can see that it is all because of the velocity gradients and the viscosity, viscous dissipation term. Okay. So just recall viscous, this is viscous dissipation term, this is viscous dissipation term. Okay. Now, and dp by dt is nothing but dou p by dou t plus u dou p by dou x plus v dou p by dou y, and this is the volumetric heat generation either through chemical reaction or radiation or electrical heating within my control volume. So now I have conservation of mass, momentum, energy equation. Now the question is, we will apply what is called as principle of similarity and non-dimensionalize these equations and see what are the non-dimensional numbers which are going to emerge while we do this equation. So in the conservation of momentum, if you just take conservation of momentum, this is your conservation of momentum equation. You can see that this is the x momentum equation. You have the inertia force, this is the inertia force, this is the pressure force, these are the viscous forces, and this is the body force. And du by dt, if you expand, you get dou u by dou t, and these are the convective terms. If you consider, let me consider steady and two-dimensional flows. If I consider steady and two-dimensional, the moment I say steady, nothing varies with time, then dou u by dou t is 0, and z term, that is dou u by z and w term, does not exist because it is a two-dimensional flow. So this term will vanish. So let me write the steady flow for steady and two-dimensional flow. The x momentum equation, I write x momentum equation. So if I write x momentum equation, you have rho into u del u by del x plus v into del u by del y is equal to minus dou p by dou x plus mu into dou squared u by dou x squared plus dou squared u by dou y squared plus mu by dou x of mu by 3 into dou u by dou x plus dou v by dou y plus f of x. So what I do is, I non-dimensionalize x with a characteristic length L. Characteristic length L is characteristic length for flow or a flat plate, it can be length of the plate. For internal flows, that is pipe, it can be diameter of the pipe, and y star is y by L. Y star, x star are non-dimensional, and u star, that is velocity u, non-dimensionalized with u infinity. U infinity is the free stream velocity. That means if you take flow over a flat plate, what is the velocity with which it is flowing on the flat plate? And v star equal to v by u infinity, and p star is equal to p by rho u infinity squared. If you do non-dimensionalization like this, if you substitute this in this above equation, if you substitute all of them here, so what is that you get is rho into u star, u becomes u star into u infinity, okay, and dou of dou x star, x is x star into length, so you have L, into u is u infinity into u star, u infinity is constant, so u infinity into u infinity, u star. Similarly, for v you have v star into u infinity, that is 1 u infinity, and dou y star into L, you have L, and dou u is dou u star into u infinity. So that is what you get. Now here again you have p, so you have dou p star, that is you have rho u infinity squared, minus sign is there, divided by dou x star divided by L, plus same way you can do mu into u infinity by L squared into dou squared u star divided by dou x star squared plus dou squared u star divided by dou y star squared plus mu into u infinity by L squared dou by dou x star into 1 by 3 into dou u star by dou x star plus dou v star by dou y star plus fx. Here I am neglecting body force. Neglect body force. There are no body forces. So now divide throughout. Throughout by u infinity squared by L. Divide throughout by u infinity. So left hand side will become rho u infinity squared by L you divide through. So if you do that, you get u star dou u star by dou x star plus v star dou u star by dou y star, that is on the left hand side, and u infinity squared rho u infinity squared by L will get. So you have minus rho u infinity squared by L into L by rho u infinity squared into dou p star by dou x star plus mu u infinity by L squared into L by rho u infinity squared into dou squared u star by dou x star squared plus dou squared u star divided by dou y star squared plus mu u infinity by L into L by rho u infinity squared into dou by dou x star into 1 by 3 dou by dou of u star x star plus dou v star by dou y star you get. So here if this gets cancelled out, okay, here what is that I end up getting? I end up getting rho u mu by rho u infinity L, and here also mu by rho u infinity L. So if I write that, so the equation turns out to be u star dou u star by dou x star plus v star dou u star by dou y star equal to minus 1 by rho dou p star by dou x star plus what is that? Mu by rho u infinity L, that is nothing but 1 by Reynolds number. If you recall, Reynolds number is rho u infinity L by mu, that is viscous inertia force divided by viscous force. That is the Reynolds number. So you get 1 by Re into dou squared u star divided by dou x star squared plus dou squared u star divided by dou y star squared plus 1 by Re into dou by dou x star into mu by 3 into dou u star divided by dou x star plus dou v star divided by dou y star. The point is, the takeaway from this is that when you do non-dimensionalization of momentum equation, the non-dimensional number which emerges is Reynolds number. So if anything which comes out of the momentum equation, the velocity distribution, the pressure distribution, all that is decided by Reynolds number. Remember that. That is what is emerging, and Reynolds number is nothing but rho u infinity L by mu. So similar exercise, let us do it for energy equation. So if you go to the energy equation, this is my energy equation. So my energy equation is consisting of temperature. My energy equation is rho Cp dou T by dou T, that is, this is the convection term, this is the conduction term, this is the pressure work, this is the viscous dissipation, this is the volumetric heat generation. So what I do here is, this is the viscous dissipation term, okay, and the pressure term, if you put that, you get dou P by dou T U dou P by dou X plus V dou P by dou Y plus 5 Q dot triple prime. For steady flows, you don't have dou T by dou T. So let me start off writing the energy equation for steady flows and non-dimensionalize that equation. So let me start with steady flows. Energy equation for steady flows. Okay. So the energy equation would be rho Cp U dou T by dou X plus V dou T by dou Y, which is the convection term, which is left hand side, is equal to conduction term K into dou square T by dou X squared plus dou square T by dou Y squared. This is the conduction term, and the pressure work is U del P by del X plus V del P by del Y plus phi plus Q dot triple prime. Phi is the viscous dissipation term, which is essentially the velocity gradients, that is phi equal to 2 mu into del U by del X whole squared plus 2 mu into del V by del Y whole squared minus of 2 by 3 mu of del U by del X plus del V by del Y whole squared plus mu into del U by del Y plus del V by del X whole squared. Now to non-dimensionalize, I take x star equal to x by L, y star equal to y by L, and u star equal to u by u infinity. L u infinity I have already defined, v by u infinity, and p star is p by rho u infinity squared, and t star is what is new for us, T minus of Ts divided by T infinity minus Ts. Ts is the surface temperature, which is assumed to be constant, surface temperature of the flat plate, let us say, surface temperature of the plate or a pipe, okay. T infinity is free stream temperature. Rest all we have already defined. So if I substitute this, now what is that I get? So first let us do for rho Cp. Rho Cp, u, if you do, you get u infinity by L, that is, you have u infinity, u star into u infinity, and dou y star, this is x, dou x star into L, and now dou t star. So what do you get? Dou t star is T infinity minus S, and Ts is constant, so dou Ts by dou x is not existing because Ts is constant. So that is what you get. Similarly, you get V star. For V star also you can pull out the same terms. Dou T star by dou Y star is equal to K into T infinity minus Ts you get when you do for dou T star, okay, divided by, for x you get x dou x star squared by L squared plus dou squared t star divided by dou y star squared plus okay, plus you have u, for u you have to write u infinity into u star divided by dou x star, that is L, for p star dou p star into rho u infinity squared. Similarly, for plus v star dou p star by dou y star. Now, for viscous dissipation term, so let us take up the viscous dissipation term. The viscous dissipation term, the first term, let us say, you can write, I think I will write directly, you can see that this is the viscous dissipation term. So, you have plus mu is common everywhere, mu. So, I pull out that mu, and your velocity squared, that means u infinity squared, and your x squared, that means u infinity squared by L squared, that is there, velocity squared x squared, velocity squared. So, you get velocity squared everywhere. So, you can write this as phi star rho u infinity squared by L squared here. So, now L squared. So, now what you do is you divide throughout with this term. Okay. Let us take up one by one and divide. So, if I take up this term, that is k into t infinity minus Ts divided by L squared into rho Cp u infinity into t infinity minus Ts by L. So, t infinity minus Ts, t infinity minus Ts. So, I have 1 by rho Cp u infinity L coming here in this term. Similarly, what do I get for rho u infinity squared? That is rho u infinity squared into u infinity by L into L by rho Cp into t infinity minus Ts into u infinity. So, what is that? L gets cancelled out, 1 u infinity gets cancelled out, rho and rho gets cancelled out. So, you get u infinity squared divided by Cp into t infinity minus Ts. So, for this term you got this, and for this term and this term you got this. So, let us write those term with those terms this equation. So, what I get here is u star dou t star divided by dou x star plus v star dou t star by dou y star is equal to k by rho Cp L u infinity into dou squared t star divided by dou x star squared plus dou squared t star divided by dou y star squared plus u infinity squared divided by Cp into t infinity minus Ts into u dou p star by dou x star plus v dou p star by dou y star plus u infinity squared divided by Cp into t infinity minus Ts, okay, into mu divided by rho u infinity L. Okay, that is what you get here. Yeah, this term I did not do. So, you have mu u infinity squared by L squared. If you divide it by rho Cp u infinity into T infinity minus Ts by L. So, u infinity, one u infinity gets cancelled out, L and L gets cancelled out. So, you get mu by rho Cp L T infinity by Ts. That is what I have written here. U infinity squared, that is, you get mu infinity, mu, that is mu u infinity squared divided by L squared into L divided by rho Cp into u rho Cp into T infinity minus Ts into u infinity. So, that I have retained. This is what I have put, u infinity squared by Cp into T infinity S. I have put this term, and the rest term is mu by rho u infinity L I have put here into 5 star. Now, this, if you see, this K by this is nothing but REPR. So, that is REPR equal to rho u infinity L by mu into Prandtl number is mu Cp by K. So, that is, you get this as rho Cp, mu gets cancelled out, rho Cp L u infinity by K, that is nothing but this in 1 by R. So, now u infinity squared by Cp into T infinity minus Ts is called Eckert number. So, what does this represent? It represents the u infinity squared means it is kinetic energy, the kinetic energy with which my fluid particle is moving, and Cp T infinity minus Ts is the thermal energy. So, the Eckert number represents how much of the kinetic energy is transformed into thermal energy when it is moving. So, I can now write this equation as u star del T star by del x star plus V star del T star by del y star is equal to 1 by REPR into del squared T star divided by del x star squared plus del squared T star divided by del y star squared plus Eckert number into this is star u star del P star by del x star plus V star del P star by del y star plus this is Eckert number and this is 1 by Re. So, Eckert by Re 5 star. So, from the energy equation, the non-dimensional numbers which are emerging are Re, Pr, Eckert number. So, the takeaway from this class is that if you non-dimensionalize momentum equation, the non-dimensional number which emerged is Reynolds number. So, the velocity profile, the velocity gradients, the pressure gradients, the pressure profile is dependent on Reynolds number. But when you non-dimensionalize energy equation, the non-dimensional numbers which emerged are Re, Pr, Eckert number, okay, where Re is inertia force divided by viscous force, that is rho u infinity L by mu. But on the other hand, Prandtl number is momentum diffusivity divided by thermal diffusivity, that is mu Cp by K, and Eckert number is u infinity squared divided by Cp into T infinity minus Ts, that is kinetic energy divided by thermal energy. That means my temperature distribution is not only dependent on Reynolds number, it is also dependent on Prandtl number and Eckert number. So this is the takeaway. So we are going to, in the next class, we are going to represent that the friction factor is a function of Reynolds number only. Here Nusselt number is a function of not only Reynolds number but also Prandtl number and Eckert number. So we will study this in detail. So much for today's lecture. In the next class, let us derive or do what is called scale analysis and try to get much more understanding on boundary layer thicknesses and the friction factor and Nusselt number. Thank you.